Here are solutions to homework set number 2 for ECE 376 Embedded Systems. The first problem looks at what are the results after each assembler instruction. Now, if you go to the assembler list of commands, it kind of explains them. Typically, you have an operation like add, and then the second one, F or W. F means take the results, stick it back in A. W says take the results, put it in W. For example, if I start out with 15, 7, and 3, and these three, W register and memory locations A and B, if I move literal 254, that takes the number 254 and moves it to W. So W changes. A and B are unchanged. I'll now take the contents of A, add it to the results contents of W, and put the results in A. That's what the F means. So 254 plus 7 is 261. Mod 256 is 5. Essentially, 254 acts as minus 2. It's 2's complement for minus 2. The two numbers are identical. Minus 2 and 254 are exactly the same bit pattern. 7 minus 2 is 5. 7 plus 254 is 5. That's kind of the idea behind 2's complement. So the number 5 gets put in A register. I'll now take A, move it to B, so 5 gets copied over to B, and B becomes 5. I'll now add, or logical AND, the literal 0F to W. So take 254, that has this bit pattern. So here's 254 in binary. I take the number 0F, which is 0000, 1111, do a logical AND. Anything N0 is 0, so these bits get cleared out. What I'm left with is 1110, which is decimal 14. So W becomes 14. 254 and 5 is 14. No, correction, 254 and 15, this guy, is 14. Next one. Let's do AND. I'm going to take W, AND it with 5. So W is 14. 1110 is 14. 5 is 0101. And the two together, I get 0100. Take the results and stick it in A. So A becomes 0100, or 4. I'm now going to OR B with W. So W again is 1110, 14. B is 5, 0101. Do a bit-by-bit OR operation. I get 1111. 1111 is 15. So that's problem number 1. Problem 2. Convert the following C code to assembler. Now these are 8-bit variables. That's what char means in C. As an 8-bit number, I've got to store 8 bits or 1 byte to each variable and put them anywhere you want. I've got 3,000 bytes of RAM, any place you want. I chose memory location 0, 1, and 2. To do this operation, hold on, we have a visitor, by the way. This is Xena. Say hi, Xena. Okay, anyway, to do this, a couple ways of doing it. I'm going to first take the number 3, move to W, so at this point W is equal to 3. I'm now going to take B, add it to W, put the result in W. So W is now 3 plus B. Again, 3 plus 2B. So I now have, oops, somebody's playing with my cord. 3 plus 2B. I'll now add C 6 times. Add. I now have 3 plus 2B, and I can't see the screen because my cat's blocking it, plus 6C. Now take W and move it to A. That's one way to do it. Second way is you can be a little fancier, use the multiply command. Move 3 to W, move W to A. I now want 2 times B. I'm going to use the multiply literal command. Move B to W, multiply W times 2. When I do that, I have a 16-bit result, product high and product low. Take the low 8 bits, add it to A. The high 8 bits, I don't have any place to put them. It's only an 8-bit number, so I lose them. Same thing with C. Move C to W, multiply by 6. Take the low 8 bits, move it to W, add those to A, put the result in A. Either one works. This one takes, what, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 instructions. This one takes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 instructions. So it's kind of a wash. Either way works. Third, suppose instead I had a 16-bit operation. A, B, and C are 16-bit numbers. Again, we have our visitor over here saying hi. Say hi, Zena. Hello. Got 16-bit numbers. Do the same operation. This is an 8-bit processor, so 16-bit operations are harder than 8 bits. And one of the tricks is there's two adds, add and add with carry. If you do base 10, suppose I have 97 plus 36. I do 7 plus 6 is 13, that's 3, carry the 1. 9 plus 3 is 12, with a carry is 13, carry the 1. I get 133. The first addition is just a straight add. From then on, it's add with carry. Same thing. I've got three 16-bit numbers, and what I'm going to do is have A is right here, and here's A plus 1. I'm going to stick A at memory location 0. A plus 1 is location 1. That's the high byte, low byte. So I'm going to first start with the number 3. I move 3 to A, 0 to A plus 1. I've got the number 3 in A. 0 in the high byte, 3 in the low byte. Now I want to add B to A. I do the same thing. I've got B plus 1, A, misspelled, B added to A plus 1, A. When I add them, that goes to C and C plus 1. High byte, low byte. I'll take B, move to W, add B to A, put the result in A. B plus 1, move to W, add it to A plus 1, put the result in A plus 1. And notice this is an add with carry. The first one's an add, from then on it's add with carry. Did that once, repeat. So I do that, so I now have two B's. Likewise for C. Yeah, I didn't do this right. Take the low byte of C, add it to the low byte of A. High byte of C, add to the high byte of A with a carry. Do that once, twice, 3 times, 4 times, 5 times, 6 times, done. And basically, integer add is a lot harder than a 8-bit add. Next problem. Do the following code in assembler. I'm going to first say A is A and 0F, move 0F to W, and it with A, put the result in A. Then if statement, if A equals 0, B equals 1. I first have to set it up. Go to the assembler list and see what commands I want to use. There's the compare, skip if equal. That's going to compare A to W. To make that A equal to 0, I first have to move 0 to W. Compare A to W. Is A equal to 0? If so, I skip. If I skip, B equals 1, move 1 to W, move W to B. If not, don't skip, and I need to go to skip over. If A is equal to 1, B equals 2. Same approach. I'm going to use the compare skip if equals. I move the number 1 to W, setting up the operation. Now compare A to W. Is A equal to 1? If so, skip. Move 2 to W, W to B. Otherwise, skip out. If A is equal to 2, if A is equal to 3. So that's one way of implementing the C code in assembly. That's using the compare skip if equals. If the test is true, I skip the next command. Problem 5 is a flowchart. Each block of the flowchart corresponds to a section of C code. This guy right here is this section. I want to make port B input, so move the number FF to tris B, which is 2 instructions. Move FF to W, move W to tris B. Clear, tris C and D. Port C and D are output. This is a label. I need a place to go to. This guy right here is that section of code. I'm going to check bit 0 of port B. That's a bit test. The CPFSEQ compares 8 bits, BTFS compares 1 bit. So I'm going to test bit 0 of port B. I want to keep looping if it's 0, so skip if set. If it's 0, I don't skip, I keep on looping. If it is set, I skip out, go here. This line actually isn't needed because that's my next instruction. I now do here, count on port C mod 6. I'm going to increment port C, put the result in port C, move 6 to W, and check, is port C equal to 6? If it is equal to 6, I skip, which is when I go to 6, counting mod 6 is 0, 1, 2, 3, 4, 5, 0, 1, 2, 3, 4, 5. If I ever get to 6, I clear it. Otherwise, I skip out. So there I counted mod 6. That's this section of code. I now want to check, is port C equal to 0? I'll move 0 to W and check, is port C equal to 0? If so, I skip. I skip and go to label 4. Otherwise, I go to label 5 down here. At label 4, I count on port D, mod 6. That's this section of code. Increment port D, put the result in port D. Is it equal to 6? If so, clear it. Otherwise, go to label 5. That's again a bit test command. Is port B bit 0 equal to 1? Skip if set. If it is, I go to label 2. If not, I go to label 1. So this is one way to implement that code. And this is rolling 2 6-sided dice. Problem 6 is implement this code. Turn your pick into a $65 8-bit operator. I can add, subtract, or multiply two 8-bit numbers. Again, it goes by blocks. Here's my initialize. Port A, B, and C are input. D and E are output. Label. I'm going to check port A and do that in a couple different tests. I'm going to check, is port A bit 1 equal to 1? If it is, I go to label 3. Is port A bit 1, port A bit 0 equal to 1? Is port A bit 1 equal to 1? If it is, go to label 4. And that's the bit test, skip if clear. If it's set, I don't skip. If it is clear, I go out, I skip over. And check bit number 2. Then my labels. Label 3, I want to add, move port B to W, add port C to W, put the result in W, move W to port D. B and C are unchanged. D becomes the sum of B and C. Skip out. Likewise subtract. Likewise multiply. Then at the end, I'll toggle port E bit 0. It's right here. And then go back to label 2. So that's homework set number 2 for ECE 376. On this assignment, you don't actually need to get the code to work. We'll be doing that on homework set 3, actually compiling your code and running it. Homework 2 for 376.